This video is about the relationship between the DFT and the DTFT. Previously, we have discussed that the DFT is a sampled version of the DTFT, but there are conditions that are required in order for that to actually be the case, and what I'd like to do is explore those conditions in more detail in this video. Let's pretend that we don't know anything about the conditions, and we just say let's take this DTFT function and let's sample it at k or at capital N points uniformly between 0 and 1 in frequency. Let's see what would happen if we were to do that. To understand this, what we're going to do is we're going to write down an expression for the DTFT. And then let's evaluate this at frequencies that are these rational numbers between 0 and 1. So here I've substituted for f and replaced it with k over n. Now, to push forward on this, what we're going to do is look at the structure of this complex exponential. It turns out that it is, as a function of n, it is periodic with period n, capital N. So we're going to do a change of variables here, and to describe this change of variables, let me illustrate what we're going to do here on a number line. And what we're going to do is let's take a particular case. Let's say n is equal to 4. So we'll have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. We could go backwards as well. What I'm going to do is use the following change of variables. I'm going to say n is equal to u times capital N plus v, where v goes from 0, 1, 2, 3, which in this case is n minus 1, and u takes on all integer values. So again, this is the n-axis here. What this change of variable does is it breaks the number line up into chunks or blocks of length n. In this case, n is 4. So it breaks the number line up into chunks that look like this. And so on. If we were to label these chunks, this would be the u equal to 0 chunk, and then within that chunk v takes on the numbers 0, 1, 2, 3, 0, 1, 2, 3. When n is 0, that's when u is 0, this quantity is 0, so n taking on the value 0, 1, 2, 3 as v takes on those values. And then when we let u equal 1, we have 1 times 4, so this is the number 4, and then v goes 0, 1, 2, 3. So n takes on the values 4, 5, 6, 7 as v takes on the values 0, 1, 2, 3 for u equal 1. And then similarly here, this is the u equal 2 block, the u equal 3 block. Back here is the u equal negative 1 block. So this is a blocking change of variables where the blocks are indexed by u and the sample within the block is indexed by v. And this is a unique change of variables. For any given value of n, let's say 6, there's a unique pair of numbers, u and v, that gives us the value 6. How do we find that? Well, u is equal to the floor of n divided by capital N, and v is equal to n modulo capital N. If we plug in the number little n equals 6, so that's 6 divided by 4, that's 1.5. The floor of that is 1, so u would be 1. And 6 modulo 4 is 2. And so, yeah, this is the v equals 0, 1, 2, 3, and so on is 0, 1, 2, 3, 0, etc. 0, 1, 2, 3. So again, v is the index within the block, and u is the index of the block. If we do that change of variables, this is the change of variables that we're going to use, then this sum on n splits into two sums. I have a sum going from on v going from 0 to n minus 1, and then there's a sum on u that goes from minus infinity to infinity. X un plus v. And then if we do that change of variables up in the exponent, we have e to the minus j 2 pi k u n over n, and e to the minus j 2 pi kv over n. Now if we stare at this complex exponential here, we see that the n's cancel, and then this is e to the minus j 2 pi times an integer, so this complex exponential just becomes 1. So if we rewrite this, we have v going from 0 to n minus 1, and okay. Now, this quantity in parentheses here is a function of v only, because we're summing on u. And if you look at this outside sum, it has the form of a discrete Fourier transform of length n. But it's not a transform of the signal x. It's a transform of another signal that is derived from x through this process, whatever this process is doing. Let's call that signal x tilde. Sorry, that's just a function of v. X tilde of v e to the minus j 2 pi kv over n. And that's a sum on v going from 0 to n minus 1, where x tilde is this quantity that you see here in parentheses. I'll write that at the top of the next page, and let's try and understand what that quantity is. X tilde is an infinite sum on u, x un plus v. And note here that v takes on values 0, 1, and so on, up to n minus 1. Well, if you think about what's happening here, this takes our original signal and it time shifts it by capital N and adds it to the original signal. And then it does another time shift by capital N and adds it to the original signal, and so on and so on and so on and so on. This in fact describes the periodic replication process. So we could say this is it's a periodic replication of our original signal, where we're generating these periodic replicas and then adding them all together. Another way to describe this is aliasing, but in the time domain. Now before, when we were talking about sampling in the beginning, we had a signal that was a continuous time signal, and we sampled it to create a discrete time signal, and we found that the result of that sampling operation was aliasing in the frequency domain. Here we're applying those same kinds of operations but in the reverse domains. Here we start with a continuous frequency signal, we sample it, and we find that we get aliasing in the time domain. So this describes that aliasing effect. I'd like to explore this with a numerical example. And I've made a picture to describe the example that we're going to look at. So let's suppose that we begin with a signal, x of n, that has 16 samples. Those samples are indexed from time 0 to time 15. And let's suppose that we arrange those in this vector, which I'm representing here by this rectangle. And so it has length 16. So the sample here at the beginning is x0. This would be sample x9. This would be sample x10, and so on up to sample 15. Now we can do several different things with that signal. We can calculate the DTFT. That's a continuous function of frequency, and we'll assume that we're looking at frequencies between 0 and 1. The other thing that we could do with that 16-point sequence is we could calculate its DFT. Now we know that when we calculate a 16-point DFT of a 16-point sequence, we're going to get a sampled version of the DTFT here. Uniformly spaced samples between 0 and 1. But I want to explore two other things that we could do with this. We could take the first 10 samples and just truncate the sequence, just taking those first 10 samples, and calculate a 10-point DFT, which would be indexed from k going from 0 to 9. Another thing that we could do is we could follow the math that we've just derived and perform an aliasing of the signal. So let's suppose that in this case n is 10, and we do this 10-point aliasing. What does that look like? Well, what that would mean is we take the first 10 samples and then we shift these last 6 samples so that they overlap the first 6. And when we add those together, we get aliasing in the first part of that signal, but the last 4 samples are unaliased. Now, if we take the 10-point DFT of that time domain aliased signal, then we know, according to the math that we just derived back here, that if we just take the DFT, or the DTFT, and we take samples, an arbitrary number of samples, even if it's an insufficient number of samples, fewer samples than the length of the signal that give rise to this transform, then we're actually getting samples of the DFT, the samples that we get is a DFT, but it's a DFT of an aliased version of the original signal. So we're using this in reverse. What we're doing in this example, just to see if it really works numerically, is we're going to take the time domain signal, we're going to alias it, and then we're going to calculate a 10-point DFT of the aliased signal. And according to the math that we've derived, these samples, this 10-point DFT, these numbers, should fall directly on top of the DTFT at these specified frequencies. So let's hop over into MATLAB and see if this really works. So I've written a MATLAB script that you can see here. I've chosen n equals 16, and I've created a complex exponential that has a frequency of 3/16. I'm calculating the 16-point DFT using the FFT function. That's x1. Now I'm going to do time domain aliasing. The first step is to select out the first 10 samples of the original signal, and then I'm going to add to that, add to the first 6 samples of that extracted signal the last 6 samples. And so that's this aliasing that we were looking at here. So I pull out 10 samples, and then to the first 6, I add the last 6 samples from above. That's the time domain aliasing. So the aliasing is confined to the first 6 samples. Now if we hop back to MATLAB, after I do that aliasing, I calculate the DFT, a 10-point DFT, of the aliased signal. And I also, just for fun, calculate the 10-point DFT of the truncated signal. Let's run this script and see what we get. So here in this plot, I'm showing several different things. First of all, the orange line that you see here is the DTFT of the 16-point sequence. And the yellow line that you see here with the X marks is the 16-point DFT of the original signal. And as expected, the yellow line falls directly onto the orange line, as we had planned. Interestingly, because this is a special, this sinusoid, this complex exponential, has a frequency that's 3/16, the samples of the 16-point DFT fall either directly on the peak or on the zero crossings. And so it's not a very interesting set of samples, but it nevertheless is the set of samples that fall directly on the function. Now if we also look at the 10-point DFT of the aliased signal, we get these 10 samples. These are the ones shown in purple, and notice that they also fall directly on the DFT, or the DTFT of the original sequence. So that shows us that the math is true. The other thing that we see here is if we truncate the signal and take a 10-point DFT of the truncated signal, we do not get samples of the original DTFT. For one, they're lower in amplitude, and that's just because there's less signal energy present. They tend to follow, in general, the shape of the original signal, but there are exceptions to that rule. So basically, the thing that we've learned from this example is that we need to use a transform that is at least as long as the data sequence itself. And if we use a transform that is shorter in length, we will not get samples of the DTFT. So here's maybe how to the take-home message from this video lecture is, let's suppose we have this signal x of n, and its length is L. So it goes from time 0 up to L minus 1. When we go to take a transform of this, we have to choose a transform length. So we have to choose capital N. So let's say x is the n-point DFT of xn. So if n is greater than or equal to L, then the thing that we need to recognize in this case is that there is no aliasing that occurs in this sum. And if there's no aliasing, then xk is equal to xf at frequencies k over n. So if we choose n over here, what effectively happens is we get zero padding of our sequence, and that's perfectly fine. This just means that we will get more samples of the underlying function, of the underlying shape that's present. But if n is less than or equal or less than L, then the samples that we get from an endpoint transform are not equal to anywhere, or at least we cannot expect them to be equal to samples of the original transform. So this is the take-home message. The take-home message, once again, is you can zero pad, but don't truncate. Don't do that. I mean, if you do, you have to recognize what we're going to get. We're not going to get that basically changes the shape of the transform of the underlying DTFT that we're sampling with our DFT. But if you increase the length by padding with zeros, then there's no problem. We don't change the shape of the underlying DTFT because all the data is present. We just get more samples than we need, than the minimum that's needed to represent the function. So zero padding is good. Truncation in general is bad. That's the moral of the story.